Does anybody have a solution already, or at least a partial solution? Maybe a solution to A? You?
5.7.
That's what I have too. How have you done it?
Is probably
Pardon?
The specific distance. That's it. The complex size,
Ah.
the length divided by
Times L divided by A. That's rho.
yeah.
And let's give the resistance a name. That's R20, right? Okay. Now what is rho again?
0.017.
0.017, and the unit? That's ohm times square millimeters divided by meters. The length is 117 meters, 170 meters, and the area 0.5 square millimeters. Okay. Now, of course, here we have the nice case where we can just eliminate square millimeters and meters. So the result is ohms. And the value was again?
5.7.
5.78 ohms. Okay. Now let's wait for maybe 2 more minutes. Maybe somebody will come up with a solution to B. You have one?
So you are 5780, we have 5,780 into 10 to the power 3. And I use this formula. And
Well, the value is okay, but where's the units? You see, that's what I told you at the beginning of the day. Always write down values and units. But you also down here, what's that? Oh, 6. Six. You try to convert the square millimeters into something else. You don't have to. If you write down the right units in this solution, here, and you just write down this as it is given in square millimeters, then you can just eliminate the square millimeters. You don't need to convert it into meters. This way, you made a mistake. It's a factor of 1,000, something like that. No, it's 1,000 to the power of 2. You are wrong. Okay, so keep in mind, always write down values and units and work with the units. Okay, does anybody else have a solution to B? Yeah?
13.27 ohms.
That's a bit too much, I believe. It doesn't change that much, actually. We are looking for the resistance at 62.5 degrees Celsius. Okay, I will just start writing down the equation. I mean, I guess everybody probably has the equation because it's on the slide.
Okay, now you just have to plug in the values. You will find alpha and beta in the table on one of the previous slides. R20 is what we just calculated, right? One plus. What is alpha 20?
92 minus 10 to the 3, 1 over 30.
That's 3. Okay. And what do I write for the temperature difference?
62 minus 20 and then convert Kelvin.
Oh, 62.5 minus 20 is 42.5. And now convert Celsius to Kelvin. Pardon?
350. Kelvin.
Any other idea? It's the temperature difference that we're looking at.
It's different, so the 1% to carbon doesn't matter.
Exactly. It's the same.
Okay.
I mean, the 0 Kelvin and the 0 degree Celsius points are different, but the division is the same. So whenever we look at a difference, it doesn't matter. I forgot to write down the unit behind this one here. This is 1 over Kelvin, right?
Yeah.
Times 42.5 Kelvin. Plus beta 20 is 0.6 times 10 to the power of minus 6, 1 over Kelvin square, times 42.5 Kelvin to the power of 2. Okay, now it's just a matter of typing in the right values. Who has a result? 6.75 ohms. So it changes, but it doesn't change that dramatically. Okay, now we know that there is a temperature dependence of the resistance and we know how to deal with it. In many cases, this temperature or this impact of the temperature is something you don't really want to see. It's a parasitic effect. And if it has an impact on your application, you have to somehow compensate for it, deal with it. But there are also direct practical applications of this behavior, like temperature sensing. You can use a resistor as a temperature sensor. When you know this equation, when you know the material of the resistor, when you know these parameters, then you know the characteristic, the temperature characteristic of that resistor, and you can use it as a sensor. Now, not all materials are very good for use as a sensor, but there's one material which is used very, very often, and that is platinum. Who has heard of PT100 resistors before? PT is for platinum, and 100 denotes the nominal resistance of that device at 0 degrees Celsius. In that case, the reference temperature is normally not 20 degrees, it's 0 degrees. So they specify the nominal value at 0 degrees. Apart from that, it's a resistor, R. It's made from platinum. It has a temperature dependence. The nice thing about platinum is, or the nice things are, that the characteristic is almost linear. So most times it's good enough to use only the linear temperature coefficient and assume that beta is 0. The equation becomes much more simple. The characteristic is almost linear. And the other nice characteristics are that platinum is very stable. It does not degrade very much over time. It does not degrade very much with other environmental parameters like elevated temperature over a long time or something like that. So it preserves its properties very well. So that's why it's used for this kind of sensor. The 100 ohm version is the most common one. There are also 500 ohms and 1000 ohms, 1 kilo ohm versions. But PT100 is the most common one. Now, how do you use it? Well, look at this circuit down here. We have the resistor, the PT100, and we bring this resistor into that location where we want to know the temperature, of course. Very often in laboratories, for instance, when you test electrical systems or anything else, you test those things under elevated temperatures, hot or even cold temperatures. You use a climate chamber for that. You put the system into the climate chamber, and there's some little opening on the side. You can feed wires through that opening into the interior of the chamber, and among others, you can use a PT100 and bring it into the chamber. You take the wires out, apply a current source or a voltage source. You will see a current flowing. You can measure the voltage, you can measure the current, you can calculate the resistance. When the temperature within the chamber changes, of course, current and or voltage will change. And you calculate a different value for the resistance. And then you can use the equation that we just used here. In that case, solve it for the temperature theta. On the left side of the equation, the resistance will be known from the measurements. You solve it for theta, calculate the temperature. Now, there's one obstacle. There's one thing which may lead to wrong results, incorrect results. When you think about this chamber again, with the opening on the side, you have the sensor inside. There's a wire coming out, and then you have your measuring instrument somewhere outside. You will see pretty long wires going to the sensor. And these wires are not ideal. They have a resistance. So the current which is flowing through the sensor is also flowing through these wires. And there will be a voltage drop along these wires. On the one side, into the chamber, and also on the other side, out of the chamber. And you cannot distinguish between the wire resistance and the sensor resistance. So your measurement may be incorrect. Well, this is why usually this circuit that you see on the slide is used. This is a so-called 4-wire measurement. The source applies current that flows through the sensor and then back to the source. Of course, you will see some voltage drop along the wire. That's indicated by these outermost resistance symbols here. But we do not measure the voltage here outside the chamber. We measure the voltage using a voltmeter and additional 2 wires. So we feed the wires coming from the voltmeter also into the chamber. And we measure the voltage directly between the 2 terminals of the sensor. So what is the advantage now? I mean, there are 2 wires. There are also 2 wires leading to the voltmeter. So where's the difference? Why can I not just connect the voltmeter here and here? Okay, here's the solution. There will be almost no current flowing in this loop. The current supplying the sensor is flowing here in the outer loop. In the inner loop, you will see hardly any current. Of course, the internal resistance of the voltmeter has to be extremely high. So you should use a good voltmeter with very high inner resistance. In that case, almost no current will flow here. You will have almost no voltage drop across these wires. You will get a good result regarding the resistance of the PD100. So that's the idea behind the 4-wire measurement. This, by the way, can be applied in many other practical cases too. Whenever these wire resistance play a role, you can try to apply this principle. Fine. There is one more exercise actually in the slide set. I will not do that in the lecture. I leave that for the tutorial. Next time we will start over with work, energy, power, and efficiency. Have a nice weekend. See you on Tuesday.